Good. Now it's my great pleasure to change from cancer and cancer modeling and microvasculature towards human movement with Elena or Lanie Gutierrez-Farewik. She's professor of biomechanics at the KTH Royal Institute of Technology in Sweden with a bachelor in mechanical engineering from Cornell University in 1995, and 2 years later she got a master in biomedical engineering from the University of Michigan. In 2003, finally, she got her PhD in orthopedics at the Karolinska Institute of Sweden. And now she's for over 20 years at KTH and obtained a position as a full professor in 2018. Moreover, she's the president of the Swedish Society of Biomechanics. Importantly, she is the founder and now the director of the Promobilia MoveAbility Lab that she founded. Sorry, I'm repeating this. This MoveAbility Lab is a physical research infrastructure to analyze human movement and has now over 20 people. Her research interests encompass the movement simulation, strategies, consequences, and assistance of children and adults with motion disorders, where she now has nearly a decade of clinical experience at the Karolinska University Hospital. Today, Lanie will give a talk entitled From Lab to Implementation, the Role of Biomechanics for Assisting Movement, where she will give us insight into her work and the work of her group at KTH MoveAbility. So I'm already sorry because we will be around 10 minutes late because we're starting later. But now I would like to give the floor to Lanie.
Thanks.
Thank you.
I'm hoping everyone can hear me okay. Yeah, great. Okay, thanks for that very nice introduction. I'll try to keep my time. Yes, as was mentioned, this is the research group. It's not a very updated photo, sadly. We need to take a new one. But there's two of us who are faculty. We have an employed lab manager who's full-time, 3 postdocs, a number of PhD students, and actually 3 who just finished. The top 3 on the right just finished in the past month and a half. We have some PhD students who are external who work with us, and visiting master's students and visiting PhD students. And they're, of course, the biggest resource we have. Besides that, we have a lab, obviously. It looks something like that. It's a motion lab. I'm assuming everyone's seen a motion lab before, and they know more or less what kind of equipment's involved. We have a pretty well-equipped lab. It's maybe not huge, but it's right in the middle of Stockholm, and we do a lot of things with it. Besides, cameras and force plates and EMGs and that kind of thing, we have different pressure sensors. We have an ultrasound device, and then we write a number of different algorithms and predictions and that kind of thing. So, just a little bit of context is that about 1.5 billion people in the world today have some kind of disability, and this number is increasing for a number of reasons, largely because the population's increasing and getting older. By 2050, the current number of people in the world who are 60 plus is going to double. Musculoskeletal disorders are one of the leading factors to sick leave, which, as we all know, is expensive to society, and, of course, a burden on the individual. We all know that mobility is a factor in overall health and quality of life. Therefore, it's a reasonable conclusion that there will be an increasing demand for technology to improve mobility. And this can have potential gains on each individual and on society, costs, everything. So here in the next few minutes, I'm going to show some of the research and goals that we have at our group to measure and analyze movement, to decode the relationship between motor and sensory function and movement performance, to predict movement performance, and to develop assistive devices. So I think this week you've been at kind of different scales. I guess I'm going to scale up a bit on the levels that you've been looking at this week. I'll try to have some focus on simulation and in silico approaches, though not only. So I've broken this down into 3 themes. The first theme is decoding motion or movement. Second theme is measuring and estimating loads, and then enhancing movement. Okay, so decoding human motion can be actually kind of complicated. So one can have, let's say, outcome measures or some kind of performance or evaluation of walking or whatever motion, and we can, you can call these measures different things. Is a goal that that the movement should be as normal as possible? Is that important? Is it maybe that one can just walk further than they could before, regardless of how normal it looks? Is it just that that someone can be more active and participate in society regardless of steps 1 and 2? There's really no answer to that question. They're all correct to some extent. And the way people move, it's influenced by, let's say, the more mechanical factors that we engineers, I guess most people are engineers, we can describe a little bit more easily. Strength, we can understand strength, and we can understand why one needs strength to be able to move. But then somatosensory factors can be a little more difficult to describe. What is a balance disturbance? What does that mean? And what equation can describe that? And then, of course, there's an influence from any kind of assistive devices, any kind of outdoor environment. Here, we're in Barcelona. You don't have icy and slippery sidewalks like we do in Stockholm, but perhaps they get wet and slippery. And that, of course, will make a difference. And then above it all is some kind of, the brain is deciding how one should be able to move, and it's using some kind of strategy. And those could be quite different or a combination of different ones. Sometimes we move the way we do because it's the most metabolically efficient. Sometimes it hurts, and we want to walk a different way so it doesn't hurt. Right. So some of the questions that I've listed here are, why do we walk like we do? You could change that to move like we do for other motions too. What happens if we have pain? What happens if we can't feel the environment around us? And again, a balance disturbance, what is that? What does that mean? And then what changes occur in tissues after a neurological injury? I actually won't go into that too much today, but it's one of the questions we have in our group. After one has an injury, how does one relearn a motion or learn a new way to do that motion? How does the environment affect the way we move, and what does it mean to have a good outcome? So humans are made to move. We were, from a very early age, without being told, we all try to get up and we all try to walk. Practically every child, a baby who's between 10 months and 14 months, gets up and starts walking if they don't have any kind of disturbance. And they all walk about the same way without anyone ever having to explain that, well, when you put your right foot, you should land on your heel and advance your left. No one ever says this to people, but we all figure it out anyway. And if we don't have any kind of disturbance in our system, we all walk pretty similarly. People have a little bit of uniqueness of their style and their, overall projection, but really the differences are minor without any kind of disturbance. So that's kind of useful. It makes it so that we can, to some extent, predict motion, or at least gait. And we do this, hopefully most of you, if you don't exactly do this field of biomechanics, hopefully you're at least aware of this human movement science and human movement analyses and simulation approaches. So one way is using an experimental or a prescribed approach in which we measure real people. They come into a lab and we put markers on them and we measure forces and all kinds of things. And from there, we can try to model, it's a real person has a lot of different tissues and a lot of different systems. We, of course, try to simplify that, and we make it into a rigid body, a system of rigid bodies usually. And we describe angles and joints and joint articulations in certain ways. And from there, we can take it the next step and describe inverse dynamics, so how the forces from the floor, what kind of resulting requirement one has on muscles and on joint loads to make that possible. And we can take it, depending on how computationally advanced we want to make this, we can take it to further levels and try to estimate forces on in specific muscles, how they change when the muscles are lengthening, shortening, and so on and so forth. But at the end, we already have the answer. We already know how they're walking. We just want to figure out how one got there. And that's in contrast to a forward approach, where we don't actually know a final motion. We start with, in this case, a modeled 3D system. Again, usually it's rigid body and linear muscles and that kind of thing. And we can put in a neural code. We can put in a neural excitement and say, okay, well, after this amount of time, this muscle should excite this much, and that muscle that much. And then the equations of motion are then, we can formulate the equations of motion, and then they're integrated in the step. And one can predict what motion is going to happen based on that neural code. So we can approach this in two different ways. Depending on goals, depending on what data we have, why we're doing this. Okay. So again, so human movement can be, it's kind of handy because it can be pretty predictable. If we have one of these systems and we give it a simple, we can put on different muscles and so on, or we can put on ranges on the knee shouldn't hyperextend and so on. And we can give it a simple command. For instance, move at a pace of 1.2 meters per second in a way that requires the least amount of metabolic energy, which in this case would translate to use of muscles. And we get a prediction that is pretty close to normal walking, and that's kind of handy, again. So we can use that because we know what the goal is. The goal often is to use as few calories as possible. If you would all get up and you'd walk from that side of the room to that side of the room, or if I just told you to go from that side to that side, you'd walk in a relatively predictable way. You're probably not going to do any crazy, you're not going to skip, or you're not going to crawl, or you're not going to do anything crazy, because your brain's already worked out that that'll require more calories per meter. Even walking slowly requires fewer calories per second, but it takes longer seconds to get there, so per meter, it's less efficient. And that's kind of handy. So we can use that to some extent. Okay, and then when we can use that, we can modify a simulation like this one, and in the next slide, the simulation is showing weak hip muscles on one side. So it's on the left side there. I think all the muscle weakness around the hip was reduced to 20% of the original. Okay, so this is now the most efficient way to walk, given that new set of circumstances. Okay, you can see when the muscles are active in this simulation. Okay, it's not normal anymore, but that's okay. This is now the best way, the most calorie efficient way to get from point A to point B if you have this set of conditions. And I don't know, does most people have someone in their life who kind of walks a little bit like this? If any of you have a, parent or a grandparent who occasionally gets hip arthritis, they tend to look a little bit like this, don't they? If you've ever pulled a muscle in anywhere around here, you probably walk a little bit like that. So it's pretty good, it looks pretty good. We can take this to, the idea with this is we would like to be able to start with, to measure a person and say, where do they have strength? Where do they have flexibility or lack of flexibility? Pain, function, that kind of thing. And we would like to be able to tie it to their motion performance at the end of the day, whatever that means. If it means normalcy, if it needs walking speed, walking quality, etc. Or in how satisfied they are. Maybe they don't care about any of the above, they're just happy or not happy. So we would like to be able to go from there to there and see if what we can measure on people, and we'd like to be able to predict their performance. So we can do it, like I mentioned, through a simulation approach, where we would try to scale and individualize each of those models to a person. Try to match their anatomy, their strength, and then a strategy, which can be tricky. It can also be useful to entirely bypass simulation, entirely bypass physics, really, and just collect a bunch of data and see if we can get from there to there. So I have examples of both. And why? Well, we would like to be able to close this loop eventually. We would like to be able to say, okay, based on that performance, what do our analyses tell us should be a recommendation for how to approach this? Should this person get a certain surgery? Should they get a certain therapy? Should they do absolutely nothing? What would happen if we do absolutely nothing? Is it going to get worse next year? Et cetera, et cetera. We would like to be able to close that loop. And like I said, we can do that to some extent with simulations. Here's another couple of simulations with a simulated plantar flexion weakness. I can't remember how much. I think it's 50% here. And dorsiflexion weakness, it's not bad. This one, I don't know. This one doesn't really look familiar to me. This one's not bad, though. You can see, I think it's the right side. It's a little bit, the foot looks a little bit heavy. It's not bad. So there can be some biofidelity between predicted and actual walking patterns, but it's a little bit difficult to validate. It's kind of hard to find a person who's completely healthy except for 50% strength reduction of the dorsiflexors. That person doesn't exist. So it can get a little tricky. We did our best with this one. In a group of people who have incomplete spinal cord injury, so injury of the spinal cord, but some muscle function left. All of these people that we tested in this study can walk, but their walking function ranges from almost normal to can take a few steps with a walker, and anywhere in between there. So we did what we could with we tried to match a model. So this model has never seen this actual person. We just tried to fit it. We tried to scale it, and the best we could, put in the strengths and so on. The only thing really we can change is strength and range of motion. It's not bad. It matches pretty well. I don't know if we can really expect it to get much closer than that. If we could do that, that would be kind of neat. Like I said, we could try to close that loop and predict, okay, what's the best way to treat this person, to maximize performance, whatever that is. The thing is, it gets pretty complicated pretty quickly. This is an animation of another subject in this group who has spinal cord injury, really asymmetric amount of sensory ability and motor ability, balance issues, all kinds of things. And I can't imagine there's a simulation in the world that's going to tell us, is going to get us here. So it gets complicated pretty quickly. So in other words, other factors are kind of difficult to simulate. Sensory function can be really difficult to simulate. Even something like if you're like me, you sometimes sit on your foot and you stand up and you can't feel anything. I do that when I'm not thinking. I sit on my foot and then I fell asleep, and I get up and I can't walk for a couple seconds because my foot's asleep and I can't feel anything. There's nothing wrong with me, but I still don't walk normally because I'm missing that feedback, right? And then it's fine after a few minutes, but that feedback is something that's actually kind of difficult to model. So, and here's an example of clinical classifications. Both of these are two different people, and both of these would have gotten the same clinical classification. And you see that there's a huge difference between them. So the clinical classifications are actually a bit useless sometimes. You can't really do too much with them. So in this case, we developed a data-driven predictive model. So we just collect as much data as we could on the people everywhere we could find in the greater Stockholm area with incomplete spinal cord injury. We collected a lot of stuff, but here I'm only showing walking speed and oxygen cost. And we measured everything we could. We measured how much strength they have and range of motion and sensitivity function and et cetera, et cetera. And put everything into a black box, into a data-driven, in this case, a SHAP explainable AI model. So we have our influencing factors, these ones in blue. So these are like, let's say, input, motor function. And we put in the output. So we already have the answers. We already know, in this case, we define performance by walking speed and oxygen cost, like I said. So we put that in there too. So we threw it all in there together, and we're trying to, the goal was to use this model to tell us for each one of these outputs or these performance measures, how much do each of those blue factors, how big of a role do they play? How big of a deal is it if one has pain or is overweight, et cetera, et cetera. And the advantage with this kind of approach is that one gets analyses on both a group level and on an individual level, which is kind of interesting here. So on the group level, again, so here's our two outputs, walking speed and net oxygen cost. We get a ranking of which of these factors make the biggest difference. And not really surprising is that muscle strength is way up there. And here, walking aids is up there. It actually slows you down if you're using crutches. Of course, if you don't use them, it's going to slow you down even more. Pain makes some difference. Sensory level makes some difference. And again, in net oxygen cost, strength makes a big difference again. It can be kind of interesting to see this on a group level, like I said. And we can also see in what way, you know, high strength is good, high pain is bad. So on the right, we get an idea of directionality of these. And then we can see it on individual level as well. So I have 2 different people in this group. And again, for walking speed on top and net oxygen cost of transport in the bottom, let's say we can start with a group average, which is here. So the group average, I guess, was something like 1 meter per second. But this person's walking speed is all the way down here, a little bit less than 0.6. So he walks significantly slower than the rest of the group. And here we can see why. So for him, he's actually quite weak. So the weakness alone shifted his expected walking speed down by 0.26 meters per second, which is kind of interesting. We know that strength is going to make a difference, but here we actually put the number on it. We can see for this person, we can estimate that this is how much difference it made. And that can be kind of interesting because if there's any way that one could approach this, can one do some kind of therapy that will improve his muscle strength? That's going to have a huge difference. Should one, you know, his BMI, for instance, is down here. It makes practically no effect. So should the therapist nag about losing weight? Probably not. Not going to make any kind of difference here. So that's kind of interesting. You know, he doesn't have much pain, which is kind of handy. And so the same idea, the net cost of transport for the whole group is here. Again, high is bad. High means it requires a lot of calories. So the whole group is down here somewhere, and he's all the way up here. And we can see what led him. So again, it's because he's kind of weak. Okay. And here's another person who's kind of the other edge of this one, pretty fast walker. So he walks much faster than the group average. And we can see because he's stronger than the average, etc. And that his net cost of transport is lower than the average. So that's kind of an interesting approach. So, all right. From there, I'm going to move on to theme 2, measuring and estimating movements and loads. So experiments are very handy. We can measure all kinds of stuff. We can measure motion. We measure muscle activations, loads, forces. We can measure lots of things. And then we need models to help us estimate the things that we can't measure directly, can't easily measure directly. For instance, internal joints and muscle forces, loads, that kind of thing. Motor control in general. We can't really measure muscle activation from every muscle. Muscle morphology, property, and compositions. This list can go on and on. We want to be able to do this as much as we can in and outside of a laboratory. It would be nice if we could all abide by some kind of theory that, you know, access to high quality analysis tools shouldn't discriminate based on your zip code. Wouldn't that be nice? And the best way to do this is probably to combine experimental and in silico methods to the best extent that we can. I'm not going to show all these projects here, but some of the, I'm going to show, let's see, 2 of these. So we're doing this in our lab with different modalities, different aims, different scales.
Heavy, but it's, yeah.
Voilà.
Okay, so on these slides, I'm going to focus on a project we have that studies shoulder loading in users of manual wheelchairs. A little bit of background is if you use a manual wheelchair, having shoulder pain and overuse injuries is kind of a matter of time. It's not really a if, it's a when. Because you're using your shoulders in a way that the extreme positions, your shoulders weren't really made to do this. And combine that with, you know, depending on what the problem is while you're in a wheelchair to begin with, if you've broken your back, you could have core muscle strength that's affected, etc. These create muscle imbalances and loading imbalance inside the shoulder. So our goal was to again, with experimental motion capture combined with 3D musculoskeletal modeling to be able to analyze this. So, you've already seen motion capture, you know how that works, and then combine it with different modeling techniques. But before we even really got anywhere on this one, we noticed a problem, that standard approaches to solve this muscle redundancy problem based on some idea of minimal effort actually don't do very well. They're not very realistic at the shoulder. So again, the shoulder itself is really complicated. That's without all the muscles. And then the shoulder joint itself, this is a humeral head and the glenoid cavity that's attached to the scapula. The ball and socket, the socket is really tiny there. So the shoulder can be unstable kind of easily. So the stability can be a real issue. In contrast to a hip. A hip is a really nice ball and socket. The femoral head's not going anywhere. But that one can glide and slide and dislocate relatively easily. So when we did our first analysis of these kind of simple motions, lifting this way and that way, we noticed that the predicted joint contact forces, if this femoral head is sitting inside that glenoid cavity, then there should be a joint contact force that more or less points inside that glenoid cavity. Do you understand what I mean? So if we take, this is a glenoid cavity, and then I'm turning it and looking at it here. So I'm doing this, flattening it this way, looks like that. So that blue circle, or that little hole, that circle right there is the glenoid cavity, 90 degrees turned. So the joint contact forces should point somewhere towards there. Oh, thanks, I'm not very tall. There we go. However, so if you see this blue circle here and this blue circle there, when we did our first analyses and put in all these different muscles there and gave it a goal to reduce, to solve muscle redundancy based on, minimal effort, that kind of thing, it predicted that the joint contact forces would be way up here somewhere. In other words, pointing rather far superior and anterior to the actual glenoid cavity, which would indicate that if this happens over a long time, it's going to be a dislocated shoulder, or at least a pretty strained one. So that doesn't really give any confidence to this kind of approach. We need to be able to model some kind of stability. So we downloaded the OrthoLoad dataset. I don't know if you know that one. There's an OrthoLoad dataset. There's people who had a joint replacement surgery, and they went along with implanting a special prosthesis that measures load. There's not very many of them, so it's kind of handy. So in a person who did some kind of motion, I think it was like this or like this, with a, 2-kilo dumbbell or something, what the OrthoLoad measured was the joint contact force should be somewhere right around there. And if we measure it without if we would try to estimate it without any kind of stability constraints, it's up there somewhere. So it's not very good. It's not good and it's not encouraging. So we worked together with AJ and Italo at Delft. We used a relatively recent version of the shoulder and shoulder model. And then we played around a little bit with the ways to describe stability. So again, this is looking at that glenoid, this one right there. So we tried different ways to force the contact force to stay inside. We tried a few simple ones saying, well, it's got to stay right in the middle, or it's got to stay within a circle, or different kind of shapes. And again, this is the OrthoLoad data set, so this is what the real contact force looks like. And we get completely different answers based on, different shapes, but none of them are actually very good. So if we force it to stay inside, for instance, this yellow ellipsoid, it just barely does that. It just stays right along the edge of it. So it's not a very good answer either. That's probably not real. It's not doing that. So we tried a different way, and that's to penalize it, so encourage it to kind of stay in the middle, and then allow it to move, in any radial direction, but give it a penalty for each, for every bit of distance traveled outside of this. And it gets a little bit better. So this is, again, the OrthoLoad, and then this is a prediction. It's not bad. So perimeter we can kind of throw away. It's not really a realistic approach. So this is kind of a spatial penalty. It encourages the contact force to stay towards the center. It's more realistic. It's not exactly super realistic. Any of these ones, though, any kind of stability approach is going to encourage the rotator cuffs more. So in general, with shoulder, you can't really think about it as just a minimal effort. It's more complicated than that. Okay. If I should skip this one. I'll take this one quickly. Another one of our projects is being able to move outside of a lab someday. We would like to be able to measure, to have a tool that people could use at home or in a rehab clinic to measure and monitor their motion. So we have made an app based on just one single iPhone or iPad. We're using the pose estimator that's built into Apple, and then we're fixing it. Actually, this video doesn't work that well. So Apple has a pose estimator that isn't bad. And Apple devices, by the way, have, besides just an RGB camera, they actually have a LiDAR that's built into them. So they are sending out like an array of lasers, of dots, like a strobe, and then they're timing the backscatter. So they do measure like a 3D topology in real time, which is kind of useful. And it happens all the time. The LiDAR sensor looks something like that one. It's like a little black hole on if you have an iPhone. Same idea with Samsung's. The thing is, it measures something, it's just not very good. So since we have a lab and we have cameras and all that, we just figured, well, let's measure everything at the same time and then just improve it. So it's kind of what we did. So we measured with Apple's, and then since we have our own, lab, we measured the systematic error, and then we wrote a machine learning algorithm that adjusts for it. So in our app, you could sort of see, let's see. So ARKit alone, so Apple's own is that orange, and the ground truth, green, that's our Vicon system, so let's say that's true enough. And then, so in our algorithm, we try to make the orange look more like the green, and it ends up looking blue. So the question is, does blue look like green there? Yeah, pretty good. Okay, so the app could look something like this. I don't know how long this demo is. Yeah. So one could prop up a phone at home. I kind of like the approach of this one. You don't have to calibrate anything. You don't have to do anything. Just prop up a phone, measure something. What happened here? So in the app, you can, measure all these things, and it goes in almost no time. And then about 20 seconds later, you'll see plots. Here's knee flexion extension. It's really hard to see anything there, but we can measure knee flexion extension, hip, whatever plots you want. And about in the app, the ARKit data goes through a cloud-based system that goes through a server that's one flight above my office in Stockholm, and comes back about 20 seconds later and is adjusted. So it's pretty cool. So I won't talk about that anymore. I'll move on to theme 3, which is enhancing human movement, largely in the form of some kind of assistive exoskeletons or different devices. Okay, so our strategy here is, I should have written minimalistic as well. We want to achieve genuine impact through minimalistic and goal-specific exoskeletons. There's already kind of a lot of larger, like full lower body models. We're actually trying to take a different approach here. If we can, sometimes you can get away with just fixing something at the ankle, and it'll kind of straighten things up further up. So if we can do that, we're going to try to do that. All right. So a couple of slides that I'll show you today are simulation-based design and control, and a little bit of human loop optimization, and a little bit of experiments. And I'm going to focus actually solely on ankle devices here. We're working on a hip device, but I don't have any slides. It's kind of a preliminary right now. All right, so one project from a postdoc, Israel Luis, is optimal lower limb exoskeleton assistance in walking predicted by musculoskeletal simulation. And these are prescribed simulations. Okay, so in general, using an exoskeleton to reduce energy cost is kind of one of the common goals that one sees in literature. And the way it works is without any kind of exoskeleton, one takes a baseline, metabolic cost or oxygen cost of walking, and then puts in some kind of torque profile, something like that. Oh, this is a gait cycle. I'm hoping you all know what this means. So during a gait cycle, one would put in a profile. So put in assistive, something that helps at the plantar flexor. Something that looks like that. Take a new measurement. Try another one. Take a new measurement. Try another one. Take a new measurement, and so on, until you've run out of time, and you figure out, well, okay, that one was the best here. Okay. It's not a perfect method, but that's kind of the standard way to do this experimentally. So one wonders, can one use simulation approach to kind of make this go a little faster, better, more efficient? Yes, I think so. So with the simulation approach, one would identify at least the hypothetically most optimal assistance. And in this way, it would be less burden. There's no use to try some probably really, really bad suggestions. Try to make it a little streamlined, a little better. So in this approach, hopefully you've all remembered your inverse dynamics from your first biomechanics class, that when you measure in inverse dynamics, you end up with some kind of net moment at every net moment or torque at all the joints. And if you recall that the net moment, usually it's due to the muscles, but if you have an exoskeleton on, then it's also due to some kind of exoskeleton. So in this one, we assume that the net torque that we see from inverse dynamics is a combination of the one from the muscles and the one from the exoskeleton. So we solve for muscle redundancy in this approach, the same way as I mentioned before. The usual way one solves, especially for muscle redundancy, to identify joint muscle forces, is with some kind of approach or an approach that assumes that that A squared, so the muscle activations are going to be as low as possible. The thing is, we tried this, and what we found that, so we did this and found that, so we solved for exoskeleton torques that result in the lowest muscle activations. They actually aren't the same as the torque that give us the lowest oxygen costs. So that, the E for here is for energy. So we cannot assume that the lowest activation squared is going to give us the lowest metabolic cost, which is actually kind of interesting. So we designed this in a whole different way. We made an inner loop and an outer loop. And then in the inner loop, we just solved the muscle redundancy alone. We do know that this actually works pretty well for the regular muscle redundancy problem. It just doesn't work well for an exoskeleton. So we solved the muscle redundancy in the usual way, and then we solved for the device aim in the outer loop. Okay, so we put in the first, design profile, and we sent it down into the inner loop, computed, okay, if we have this kind of profile, what would the muscle forces and activations look like? Sent it back up, and computed metabolic cost, and back down, and up again, and down and up again. Okay, so on the outside, we're trying different device aims, and on the inside is muscle redundancy as usual. And here we can try different device aims. We tried the minimal metabolic cost. We played around with a few different minimal joint torques, forces, et cetera, just to see which one kind of works, which one, what difference does it make? And actually, does it make a difference at all? And which one actually matches experiments best? Okay. All right, so here what I'm going to show you is just optimal plantar flexure assistance for different devices and different goals. Again, these were prescribed simulations based on 12 perfectly healthy PhD students and postdocs, I guess, from our lab. No, actually, I think these were various personnel who walked at a preferred walking speed. Again, we solved the inner loop with direct collocation. And then the outer loop, we used a Bayesian global optimization approach. And then we tried for different, so if we have a device that's supposed to minimize the muscle activations versus metabolic cost versus minimal moments. And by metabolic energy cost, this is just a model. So this is based on the muscle activation and whether it's lengthening and shortening and how fast and so on. So oxygen, the energy rate is based on work rate and heat rate. So if the muscle's active at all, there is a heat rate. But the work rate depends on whether it's getting shorter or longer and how fast. So it's most costly with fast concentric activation, and it's actually free with eccentric. Those cost nothing. Okay, and then we tried a few different assistive devices. We tried an active one. In other words, we just let that profile be whatever. It could be, you know, up wiggly and that. And then we tried a passive and a quasi-passive device that could look like a spring, let's say. So if it's a spring, our passive device would look like a spring, so the amount of torque is directly in relation to the angle at the ankle. Okay, so an active one, the profile could look, you know, almost like anything, a continuous curve. We gave it 4 different parameters: the peak torque, the timing of the peak torque, the rise, and the fall timing. So we tweaked around those 4 things. A passive, again, you could think of it as like a torsional spring. So on top, this is the ankle angle. So whenever there's dorsiflexion, there's some kind of moment being provided by this torque. Also, think of this as only unidirectional. So we're only doing anything when there's dorsiflexion. It's not doing anything when there's plantar flexion. And then a quasi-passive one, same idea, but we just have this sort of zone in the middle where it's on, and then it's off out here, so we don't get any kind of torque when we don't want it. Okay? And then we did this in the bi-level optimization, so we have our outer loop and the inner loop. So on the outer loop, again, I'm only showing here the assistance for minimal energy. So this is a change in metabolic energy. And then the inner loop is the activation squared. So we started with one and looped through. I'll show how this looks. So different profiles. Each one of those is the outer loop going to the inner loop and going back out. So each one of those points is outer loop and inner loop. And then I think we did, I don't know, 100 or something different profiles, and found the one that gave us, it's that profile right there that produced this, that predicted the lowest amount of, or the highest change in oxygen cost, or the biggest reduction in oxygen cost or energetics. What's interesting is this actually wasn't the one that resulted in the lowest muscle activation, which is kind of interesting. Okay. So we did this for the active, for the passive one, and for the quasi-passive one. And let's see, so the regular inverse dynamics, the one you're all used to, is the one in black. So this is the net moment. So if we would give an exoskeleton a goal to minimize muscle activations, then that green one is the one that it predicts. That's the one that minimizes muscle activations the most. But if we ask it to minimize metabolic cost, then actually we get that red-orange colored one. So it's a completely different one, which is kind of interesting. From there we can go, obviously the orange one actually minimized or reduced the oxygen cost the most, or the metabolic cost the most. Not surprising, that's what we asked it to do. But there's a pretty big difference. Same idea, quasi-passive and passive, I won't go into too much. But in general, if we want to reduce energy cost, we probably need a motor. The passive ones actually don't do anything. We can't predict much potential at all for these passive ones to minimize, to reduce metabolic cost. Not much, 1% maybe. So we probably need a motor, and we probably need to have an outer loop that specifically targets metabolic cost. We compared this to experiments using a human loop optimization, so they tested people and measured and so on. And again, this black one is, regular, the net moment, and that's that orange one I showed you from the slide before. The predicted profile that we found would look like here, versus this pink one, which was what they found experimentally. The magnitude doesn't match very well, but the timing matches extremely well, which is kind of interesting. That it's kind of a late onset and then a peak rather late, and that's because that specifically targets the concentric contraction of the soleus. If you just looked at activation, it doesn't consider that some activation is expensive and some is not. But here, if we ask it to do that, then it targets the concentric contraction of the soleus, which is costly in walking. So that's kind of interesting. We found that incorporating an explicit aim makes a difference, hypothetically. So, not too many slides left. So do we need experiments? Can we just stop altogether? Can we just simulate everything? Well, there's a few things that are kind of hard to predict. Adaptation, heterogeneity, even in populations that should be kind of similar, and that in motor disorders, it's complex. So, for instance, we have one of these. This is a device called a biomodem Spark that we bought. It's a ankle exoskeleton that you could put in different profiles, and we used it for plantar flexion assistance on a few different people, on a few healthy people. So we have a baseline metabolic cost here in green, and then we put this one on where it hypothetically should assist. It should give a plantar flexion support, and it should make it easier to walk, or at least reduce your metabolic cost. The thing is, it doesn't. After a minute, the metabolic rate actually went up. 20 minutes later, okay, it starts to drop now. And another 20 minutes later, oh, finally, the metabolic cost actually reduced compared to baseline, but it took a long time to get there. I don't know what would happen after another 20 minutes. It's probably going to plateau out at some point. These are kind of hard to do because it's pretty boring to walk for 40 minutes at a constant, it gets, after a while, that also has to go in there. It's kind of boring to do this. So, adaptation is tricky. It can take, I don't know, minutes, hours, days, who knows? Okay. And then, in a different project, we have made an ankle exoskeleton that is to assist people in drop foot, following a stroke. And we designed it, again, kind of minimalistic. There's 2 cables. They go from a waist, the motor's on the waist. These cables go via a strap on the calf, and then they hook onto the shoe. So in the sagittal plane, it's supposed to lift that ways. And then we have 2, because in the frontal plane, we want to be able to go that ways too. Sometimes with stroke, you have, there can be frontal plane problems too. You can have a weakness, so it's kind of hard to lift up the foot, but you can also have spasticity, which makes the foot kind of do that too. Okay, so in this, we did feasibility trials and proof of concepts on 6 people with a chronic stroke and some kind of drop foot gait. They're a little varied among them too. And the control profiles are, in this case, only magnitude and ratio of the torque to those 2 cables. So they just turn on and swing, and then turn off again. They're on and swing, and then just turn off just after the foot's back in contact with the ground. And without an exo, here's one of our subjects. Oh, that thing's in the way. I don't know how to get this bar out of the way. I don't know. Let me try that again. I don't know, it's laggy. I guess you're going to have to take my word for it. No, the bar's in the way. I can't see anything. I can't get the bar out of the way either. I can try. If you're curious, come to me at lunch, and I'll try to make it play without these bars. I don't know what happened. All right, so we did this in a human-in-the-loop approach. We don't have any kind of simulation. We don't have any kind of physics at all involved. We just put on something, and we tested, and we tried again, and we tested, and we tried again, and we tested. And we found that in our 6 people, we could do this. We could lift it. We gave it 2 goals to improve symmetry of foot position and step length. Oh, and I really wish these played. Try one more time. I don't know. Okay, so in our 6 different people, you have to believe me that we could improve symmetry, foot position, and step length. We could lift up that foot, make them land a little bit better. But the control profiles we had to put in were extremely different between these 6 different people, between these 6 people who are relatively homogeneous in this group. And what we defined as the best profile, the one that achieved these goals the best, it didn't actually always agree with the one they themselves rated the highest subjectively. So sometimes whatever felt best didn't objectively perform the best. So that's kind of interesting too, that the way people perceive is kind of individual and a little unclear. Okay, so in conclusion, in silico approaches are extremely useful, especially for things we can't measure. They enable analyses of single or combined factors on performance. They're really useful for performing sensitivity analyses and even perhaps for interactive effects. You can't do that on a person. You can't, make them weaker and make them stronger. You can't do that. And then, of course, I've showed that they can make a experimental burden quite a bit faster or lower when developing assisted devices. By combining the two, you get some sort of a magical effect. You can do all kinds of detailed analyses on muscles and joints and loads and that kind of thing. Do lots of fun stuff. Sometimes you could bypass simulations altogether. It works too. It can be useful to connect, like I said, the dots between symptoms and performance. And, however, I think that for the most part, experiments are going to be necessary eventually because people are complicated and unpredictable, and they're definitely not rigid like a lot of our models try to make everyone be. And that human device and interaction forces and that kind of thing, they can be difficult to model accurately and certainly difficult to model the perceived comfort. So with that, thank you very much. Again, thanks to my team, and if you've happened to miss it, we're hosting ISB in a few weeks, in case anyone hasn't booked a ticket to the ISB in Stockholm, late July. We have, at this point, I think, almost 1,500 participants. So it's going to be a big conference. With that, you can welcome any questions.
And we'll use that one for the public. That's okay.
Thank you, Lanie, for this very impressive and interesting talk. The public is the time is open for questions.
I wanted to ask about the adaptability to the exoskeleton that you show a graph where after 20 minutes the energy consumption was higher but then got lower. This is like the first time the user get in contact with the exoskeleton?
Yes.
Or is it like the second time or?
That was the first time.
Okay, so then...
It's a good question. We should have done the same thing the next day, and the next day, and the next day.
Yeah.
That's just data from like 2 weeks ago, so we're on it.
Ah, okay.
But like I said, it's kind of hard to find someone who's willing to walk for an hour and a half, days and days in a row. I mean, it sounds like a funny problem, but it's a real problem. It's just kind of boring.
Okay.
It's boring to do this, right? But that's just once.
Yeah, well, that was my question.
Yeah. Probably the next day it goes a little faster, I hope.
For more questions?
Actually, I have one. I'm jumping in because it's related. Yeah, so does it really make sense then to have such short windows of observation in the lab? So I mean, for example, when they want to monitor people, so for cardiac disorder, so you need to bear a holster during 24 hours because they need that amount of time acquisition. So do you think it would be more conclusive whether you just leave the device so during several days, for example, to the user, and then you would make a measurement before you leave the device and after you leave the device after several days?
Sure. Lab tests are usually to try to find some kind of optimal, so you still want to, you can't send them home for a week with one profile and then with another and then another. At some point it's not really feasible anymore. So of course lab, experiments are always going to have a purpose, but they only give you immediate responses. So yeah, of course one should be able to send it home. Ideally one would send it home with them and test, okay, so we saw good response on day 1, what's it look like on day 7? Of course. The thing is, yeah, it gets kind of hard to vary things at that point.
But then why don't you do that? Because the prototype doesn't allow it because it's not robust enough, or it needs to be used under supervision, or?
Yeah, I mean they're prototypes, so at least on the video that didn't work of our ankle device, the battery time on that one's pretty good. We probably get a good 4 or 5 hours out of it. But if we sent it home with someone, I don't know if they can put it on right. Ethically, with the MDR laws, it can actually get a little bit tricky to send devices home. I mean, it's not a very good excuse, but we can't call these medical devices. We have to call them, experimental devices. And so there's kind of annoying regulatory hurdles there too. But yes, I mean, it's a good point. It would be nice to be able to send these home. And the first proof of concept ones for our drop foot device, this was just to see if there's anything here. Is there anything to even spin on? And we do think there is. So hopefully in the next year or so, we are going to try to send it home with them, or at least try to have them use it 7 days in a row and see how it looks. Maybe not all day, but for a little while during the day. And then test different, they can't just walk back and forth on our floor. They have to go try to walk up and down hills and stairs and all that kind of things too.
More questions? Well,
Hi, this might be like a relatively general black box question, but earlier talk when you were talking about using simulations and then comparing, or then you also had strategies with using machine learning. Do you see a situation where using OpenSim or other simulations like those would just like disappear or never exist because they're getting replaced by machine learning methods? Or do you think there will always be some sort of, at least in the near future, let's say, there will always be a place for simulations like those?
I think it's a good question. I think it depends on what the point is or what the goal is. If you just want to see, for instance, how a certain symptom, what effect it has on an outcome, I don't know that you really need all the physics in between there. Maybe you don't need to know how fast concentric excitation of the soleus is. Maybe you don't need to know that. But if you do need to know that, then yes, you'll need some kind of model, OpenSim, whatever. So it depends on what the question is, I guess. I guess there's plenty of goals where you can bypass OpenSim, physics altogether, but some where you certainly can't. And a lot of different approaches are combining the two, physics-informed neural network kind of a thing, where we've done this too before. We don't just input things like signals into a machine learning algorithm. We actually run it through a model first, and then we input speeds of concentric or eccentric contractions, that kind of thing. So it depends on how much sophistication one needs for the question or for the answer. I don't know if that was a good answer or not, but do you know what I mean?
Yeah, no, I understand. Thank you.
Yeah.
we have still time for one short question. Well, I have some, but I will ask you then later on in the break so that we can have lunch sooner. I would have one question which might be the most interesting one. Maybe I missed it, and maybe you said it and I missed it, but you were talking about the very interesting cooperation between Apple and you, like to optimize this app, right? So is there any plan to get somehow feedback out of this app to try to improve public health through it? Yeah,
good question. I wouldn't call it a collaboration, I wish.
Okay.
I think Apple should buy us out for, I don't know, a few million. No. The thing is, Apple doesn't do that. That's not their business model. They don't like, they release an app store and say, do whatever you want, sadly. I don't know that they fund any or sponsor any kind of research for this kind of thing. But yes, we have an open case with our innovation office, and we have a kind of a business coach who's going out, and he's talked to different potential partners to see, where could this actually make a difference. So we're probably he's gonna talk to one of those systems that owns kind of like the medical journal systems in Sweden, if they would want to license it out. If it could be useful to, the question is like, if you have a rehab, if one of you tears an ACL or something, and then you go home for 6 weeks. Right now, there's the niche we're looking at is rehab. So if you go home with your ACL tear, your physical therapist is probably going to give you a list. It's going to say, do this 20 times a day or 100 million times a day, walk down to eccentric training, this and that. Whether you do it or not, who knows? Whether it's working or not, who knows? And then, if you don't go into a lab all the time, there's really not any kind of remote therapy. Your therapist might call you up and say, how's it going? Are you doing your exercises? Keep it up. Talk to you next week. So there's like a black hole of, there's no follow-up versus, being able to come to a lab every single day and do a follow-up, which is not feasible either. So that gray zone there is kind of what we're trying to explore. And the idea is, once a week or whenever you feel like it, you can set up your phone and see, okay, am I able to flex my knee a bit more this week than I could last week? Is it moving in the right direction? It's not going to be perfect. It's not going to be like, 3 degrees of precision. If you need 3 degrees of precision, you need to get to a lab. If you can get away with 5, okay, this might work. And then track progress over time. I think it could also make it a bit more interesting. I don't know if you've ever had an ACL tear or one of these things. Physical therapy can be kind of boring. So if this could be a little, something a little more interesting, kind of an avatar guided thing, whatever works, right? So we see sort of a few different ways to do this. So we're talking to a business coach who can see what's possible. And I like the approach. I like the idea that's easy. I guess some of you have seen like OpenCap, which is definitely better than what we have. OpenCap with 2 calibrated iPads or iPhones is definitely better. The thing is, it's still a bit of a threshold. You need to set up 2 iPads and then, sync them with a Mac with a QR code, and you have to have a calibration, like a checkerboard. And it's very cool. It's definitely very good, but if I'm picturing like my 85-year-old mother-in-law, she's never going to do that. So if we could, there's, the lower functional, the people who aren't going to do that, they might actually could set up their phone and do a simple test. So that's kind of like the easy approach I like.
Okay, thank you very much, Lanie, for this really nice hour with you.
Laura, if I may, I have last burning question.
Okay.
We can start a little bit
You
later.
poor people, you're hungry and you need caffeine.
Yeah. No, first the app stuff is really great.
Thanks.
So, but I had a bit of technical question. So, at the beginning of your talk, so when you were showing different videos, so the arms were rigid, they were not swinging, and then I guess the swinging of the arm also then contributes then to the optimization of muscle activity over the trunks, and it helps. So, are you taking the upper body into account in order then to make your minimization of muscle activation for the trainings of the entire algorithm?
Yes, and we're trying to kind of simplify as much as we can. So we're not having, we're trying to replace the upper body as more like a torque-driven, and then the lower body we have individual muscle-driven joints. But on the upper body, we're trying to keep the computational time down. And I mean, the musculature is pretty complicated. So yes, and it definitely makes a difference. It's really hard to know what's correct. What's that?
The psoas would be super important.
Yeah, the psoas is super important. I'm thinking these ones here, core muscles, that kind of thing. It's kind of hard to get right. It's hard to predict those well. If without any kind of constraints on them, sometimes it'll really throw the arms out a lot, because you can't save on muscle activation on the lower limbs if you really throw your arms out. The thing is, it's not really realistic. So it's kind of hard to get that right.
There are some machine learning techniques. I don't know if you went through reinforcement learning. where you have then this reward function, and then so basically that's so the machine learning algorithm so auto-regulates what it should take and what it shouldn't take, so depending on the reality of the case. So is that a direction you're exploring in order to consider then this?
We did in a paper. I don't have any slides that showed that. We did that before a couple years ago.
Right.
The thing we simplified quite a bit there, though. I'm almost sure we only had torque generators, so we didn't have individual muscles, at least on the upper limbs. But yeah, I mean, this was a couple years ago now, so maybe our computational efficiency is better now.
Okay, great.
But they work.
Okay, but
Okay,
now,
thanks.
please thanks the speaker again. Thank you very much, Lanie.